This video will cover the topic of quadratic inequalities. First, let's review the terms for quadratic function, quadratic equation, and quadratic inequality. Recall that the quadratic function is represented by the function f of x is equal to ax squared plus bx plus c. This is also known as the standard quadratic form. The graph of a quadratic function is that of a parabola. We can also evaluate the function at particular x values. For example, we can find f of 2 by letting x equal to 2 and substituting it into the quadratic function, so that f of 2 is equal to a, and in parentheses 2 squared, plus b, and in parentheses 2, plus c, which would give us some y value, and the point would be parentheses 2 comma some y value. This point will be on the parabola, which is the graph of the function. We will denote the quadratic equation to be in the form of ax squared plus bx plus c is equal to 0. In this situation, we will be asked to solve for x values in which the function will yield a y value of 0. In other words, we will be looking for a point or points on the graph for which the y value is 0. These are the x-intercepts of the graph, and in turn, the x values of the x-intercepts are the zeros of the function. Therefore, our solution set will be the numbers in curly brackets separated by a comma. A quadratic inequality will be comparing the quadratic function to 0. This comparison can state the function to be greater than, less than, or greater than or equal to, or less than or equal to, meaning that we are looking for what parts of the graph that are greater than, or less than, or greater than or equal to, or less than or equal to 0. Another way to see this graphically is to ask, for what x values is the graph of the quadratic function at, or above, or below the x-axis, depending on the inequality symbol. The solution for quadratic inequalities will be the intervals of x values. Let's take a look at the following chart regarding quadratic equations and inequalities. The first row is showing quadratic functions or graphs that have two x-intercepts that break up the x-axis into three parts. If you have a quadratic equation, your solution set will be in curly brackets and will contain the x values of a and b in this case. If we look at the inequality of the parabola opening up, that of f of x is less than 0, we see that the points of the graph in between the values of a and b are below or less than 0. This means our solution set will be the interval of, in parentheses, a comma b. The x values in which the graph of the quadratic function is below the x-axis. We can also see the following inequality of f of x is greater than 0. This means we are looking for the x values in which the graph is above the x-axis. We can see that these two parts of the parabola are above the x-axis, so we need to state that these two intervals as our solution as noted here in the chart. Take a few minutes now to look at the other graph on the same row. You will see that the graph of the parabola opens downward and changes the solutions for the inequalities, but not that of the equation, as the x-intercepts do not change, but the portions of the parabola above or below the x-axis changes. The second row of parabolas illustrate the situation in which the vertex is on the x-axis, in which the graph has only one x-intercept. Notice here that the quadratic equation has a solution set of only one x value. One graph is opening up and the other is opening downward. Let's take a look at the parabola opening upward. For the inequality of f of x is less than 0, we are looking for the portion of the parabola that is below the x-axis. From the graph, we see that there are no portions of the parabola that are below the x-axis, so the solution set is empty, and that is represented by the null space. The inequality of f of x is greater than 0. We are looking for portions of the graph that are above the x-axis. We see that all but the vertex is above the x-axis. The vertex is on the x-axis and not above. Note here that if this was f of x is greater than or equal to 0, the vertex would be included in the solution set, changing it from the two parts shown to all real numbers, or from negative infinity to positive infinity. In the row, the downward parabola result is similar solution sets. We are going to have to pay close attention to what values the inequality is requesting. Finally, let's look at the last row of parabolas. We see here that the parabolas do not touch the x-axis at all. This means that there are no real x-intercepts or solutions for the quadratic equation. But we take a look at the quadratic inequalities, and we see that looking at the upward parabola, we can ask for f of x is less than 0. That means we are looking for parts of the parabola that are below the x-axis. From the graph, we see that there are no parts of the parabola below the x-axis, but we do see that the entire parabola is above the x-axis. So for f of x is greater than 0, the solution set will be for all x values, or all real numbers. In interval notation, we would have to have it from negative infinity to positive infinity. You should be able to see a similar situation for the downward opening parabola in this last row. Let's talk about solving quadratic inequalities. There are 3 steps to solving these inequalities. The first step is to solve the associated equation. In our case, this means you need to solve the quadratic equation of ax squared plus bx plus c is equal to 0. We have covered many ways to solving quadratic equations, such as using factoring along with the zero product property, the square root property, completing the square, and the quadratic formula. After you find the zeros of the function from step 1, step 2 will be to plot these values on the x-axis or number line to identify possible interval solutions. Step 3 will be to determine which of the possible intervals are part of the solution. We can do this by testing values from each interval into the original inequality to see if it makes the statement true. Or we can use our logic from the previous page. Let's use these steps in the following example. Example 1. Solve the quadratic inequality of x squared minus x minus 12 is less than 0. Step 1 is to solve the associated equation of x squared minus x minus 12 is equal to 0. Try solving this one by factoring. We find that the equation can be written in factored form of in parentheses x minus 4 times the parentheses of x plus 3, and that equals to 0. Setting each factor equal to 0, we can solve for x in each situation. Our solution set for the quadratic equation is negative 3 and 4. For step 2, we place the solutions we found above on the number line and state the intervals created. Here we find that the number line has 3 intervals, which are from negative infinity to negative 3, negative 3 to 4, and from 4 to infinity. Notice that all these intervals have parentheses, as the inequality we are solving does not have an equal to. For step 3, we need to determine which of these intervals are part of the solution. Let's use our knowledge of graphing quadratic functions to determine which intervals are part of the solution. From x squared minus x minus 12, we know that the parabola opens upward, So I'm going to draw a parabola going through -3 and 4 on my number line. Now let's answer the inequality. For what values of x is the parabola less than or below the x-axis? From my sketch, we see that this portion is below the number line, so the solution set is the interval of -3 to 4. Another way is that we can test which interval is part of the solution is to test the x value from each interval into the original inequality to see which will produce true statements. So for the interval of -3 and 4, let's test x is equal to 0 into the original inequality. So we're going to have 0 squared minus 0 minus 12, and is that less than 0? And this simplifies to -12 is less than 0, which is a true statement. So the interval of -3 and 4 is our solution. If we would have tested the other intervals, we would have found false statements, and they are not part of the solution. Now let's try one more example on the next page. Example 2. Solve 2x squared is greater than or equal to -5x plus 12. First, we need to place this inequality in standard form by adding 5x to both sides and by subtracting 12 to both sides of the inequality. This will give us 2x squared plus 5x minus 12 is greater than or equal to 0. Step 1 for solving quadratic inequalities is to solve the associated equation. This means we need to solve 2x squared plus 5x minus 12 is equal to 0. We will solve this by factoring, so let's factor 2x squared plus 5x minus 12 into the parentheses of x plus 4 and the parentheses of 2x minus 3. And this is equal to 0. Using the zero product property, we can conclude that x plus 4 can equal to 0 and 2x minus 3 can equal to 0. Solving these equations, we find that x is equal to the solution set of -4 and 3/2. For step 2, we need to create a number line or x-axis and graph our solutions found in step 1 on it. This will create the intervals of -infinity to -4, -4 to 3/2, and 3/2 to infinity. Note that these intervals are including the values of -4 and 3/2, since the original inequality states that the values can be greater than or equal to. For step 3, let us imagine the parabola going through our x values of -4 and 3/2, so we can determine when it is greater than 0 or above the x-axis. From the inequality of 2x squared plus 5x minus 12 is greater than or equal to 0, we can see that the graph will open upward, since the coefficient of x squared is a positive 2. From the graph, we see that there are two portions of the graph that are above the x-axis. Once during the interval of -infinity to -4, and again during the interval of 3/2 to positive infinity. We can also test the interval in the middle and see that it should result in a false statement. Let's test the interval of -4 and 3/2 and choosing a number that is in that interval. A good test value in this interval would be the number 0. So let's let x equal to 0 and evaluate our inequality of 2x squared plus 5x minus 12 is greater than or equal to 0. To see that we get 2, and in parentheses we're going to put 0 squared plus 5 times 0 minus 12, and we want to see if it's greater than or equal to 0. When we simplify this, we get -12 is greater than or equal to 0, which is a false statement, since -12 is less than 0. Since the middle interval is false, we can conclude that testing the outside intervals will result in a true statement, making them the solution set of our inequality. Finally, let's state the solution as the interval of negative infinity to negative 4 inclusive, union including the 3/2 to positive infinity. And this concludes this video.